I feel I'm quite well placed with being part of the MRC and to discuss some of the use cases for manufacturing and of causal inference. So in recent years, there's been a push towards smart manufacturing, and this is exactly what it sounds like. So we've got a lot more data than we used to have, and it's a question of how we can use this data to optimize our processes. So that starts with sensors on machines. So these sensors here, I won't go into what these mean today, but the main thing is the data we collect during process is informative of its end quality. As well as this, we've got documentation, scheduling systems, so it's all quite rich data to work with. And we want to use this somehow to automate our processes and do feedback loops and things like that. So yeah, and for the first time, really, we can see the entire process of making something from start to finish. So that's really helpful. So manufacturers asking causal questions. I think a lot of business questions are inherently quite causal. To give an example, if I was to change my coolant type of my machine, would I see it return an investment for that? So coolant is water and oil that you spray on the machine where the drill hits the metal. That would help control temperature and control warping. So I think that is quite a causal question, maybe like a treatment effect question, but it's pretty more like counterfactuals and so forth. So today I'm going to focus mainly on metal machining, which is where you get so block of metal and you use a miller drill to take away layers one at a time until you get to a final shape. Manufacturing is much larger than this, obviously, but this is kind of a subset. This is a forging here on the left, and then on the right is the end part, which is a turbine blade disc thing. So yeah, the main way manufacturing would answer causal questions in a minute is through designs of experiments. So a DOE is where you take your input parameters and you choose various levels of those, and you could do enough of these DOEs with these trials, and you get a sense of how the factors combine to get an end result. So here we've got cutting speed, feed rate, and depth of cut, and on the right there is surface roughness. So on the left, those parameters mean essentially how aggressive are we cutting through the metal. So you can imagine the more aggressive we cut, the more feedback we might get from the machine and the more resistance it'll give you. And surface roughness is how wavy is the metal if we zoom in really closely. So that's something we're trying to control for. So we do enough of these trials and we can get a causal understanding of this process. And my claim here is that this causal understanding is, it helps you know the optimal parameters for your machine, and that saves the most out of money. So it'd be great if we could really do these DOEs or answer the same types of questions without having to do quite so many trials. And I think this is where causal inference can come in. So I'll quickly touch on why I think machine learning is maybe not the way to do this. So manufacturing is a really high-risk area. Just like medicine, there's human lives at stake. In something like aerospace or automotive, there's definitely a lot of cost involved. This part down here on the right, that costs maybe up to £1 million to get to that stage alone. So you really want to make sure that the models you've got, you can trust those models. And any decisions it makes, you can know how it got to that stage. So there's really a big emphasis on how can we make reliable, data-driven decisions. So yeah, during my PhD, some of the ideas I've got, what I'm working on in a minute is process optimization. So I've got a process here. This is making of some metal parts. And what we're going to do is make the metal parts and we'll check them against some quality metrics. And then we're going to decide, should we accept them for our plane or whatever, or should we scrap them because they're no good? And that's based on some defects you'll observe. So any part will normally start with a forging. This is some cast or molten metal that you do with various temperatures into a rough shape, and then you will machine that until you get to the finest shape that you want. So yeah, these forgings and these temperatures are really informative of the conditions of that piece. What you don't know critically is the microstructure of that piece. So the microstructure is the invisible residual stresses that the piece holds. And you can't really know these without doing cutting it open in half in practice. So if you cut it open, you're not going to have a piece anymore. So that's not really knowable. I put it down there as a latent confounder. What we do know is anything we measure in process, like sensors, anything we take into quality metrics. So we would know surface roughness. We can intervene on our machining parameters here. So to give an example, we could slow down our cutting speed, and that would reduce vibration along with other things as well. And then reduced vibration can lead to reduced surface roughness. So that would come at the expense of machining time. So with all this data, we're going to decide, should we accept or scrap our part? And it's really a question of how can we make the optimal interventions under these latent confounding conditions. So yeah, other examples here. I won't get to all these today. If you're interested in any of these, come and talk to me in the post session today. My email's down there as well. So I'll just say thank you for your time.